7.4, we're going to be dealing with equations and inequalities that involve logs. So when we see like logarithmic equation, the definition of that is literally an equation that somewhere in it has some sort of log expression. So this one, for instance. And when we're solving log expressions that only contain one log in it, what we're going to do is we're going to use that conversion back and forth between log and exponential. All right, so let me write something down that will hopefully be helpful for you. If you guys remember, so this is the exponential form when we have y equals b to the x, and we can translate this back and forth between log and exponential. This becomes x equals log base b of y. All right, so these pieces right here, this translates back and forth. If you're in this form right here, you can translate it into this form and vice versa. All right, so when we're in a form like this, we want to translate from this form into this form, and that will allow us to pretty quickly solve for whatever variable we're missing. So this one, we will take this value right here, the base, and then kind of like flip-flop this piece and this piece. So we will have 8 raised to the 4/3 power equals x. So we were in this form, now we're translating into this form. So like the 8 right here became the base, the 4/3 on the other side became the exponent right here, and then this y became, or I'm sorry, this y became this right here. All right, so we're just translating into exponential form. Now we need to know what this is. All right, so to know what this is, we need to go back to chapter 6 and remember that this 3 in the denominator becomes the cube root. So this is the cube root of 8 to the 4th power. All right, so now we can either do the 8 to the 4th first, which would be a very big number. I would recommend against that. Or we could take the cube root of 8 first. So cube root of 8 first is 2, and then raise that to the 4th power, we get 16. All right, so our value of x that we are looking for is 16. Okay, so really what we did to solve those, and this is what you'll do for every one of these types, is you'll turn it into exponential form and then solve it that way. All right, if we have logarithmic functions where we have 2 different log expressions, we're going to use the following logarithmic property. We can say then log base b of x is equal to log base b of y if and only if x is equal to y. All right, so if you see these 2 exact same log expressions, they both have the same base, we can say if this is true, then this is true. We could also say if this is true, then this is true. That's what the if and only if means, is that the if then goes both ways. All right, so let's look at an example like that. This is a multiple choice example, so we'll be able to test out all our different options here. So here, notice we have log base 4s for both of these, so what we can do is just say that the stuff on the inside must be equal to each other, and that's just based on that property that we just wrote down. All right, so since this is a quadratic, we're going to solve it by, or we're going to at least attempt to factor. We might have to use the quadratic formula. So we want to get everything on one side. So we're going to add the stuff from the right. So add 6x to both sides, add 8 to both sides, and then we'll be able to solve this by factoring it down. So we start with x and x, and we want to multiply to 8, add to 6, so that would be positive 4, positive 2. So our 2 answers would be negative 4 and negative 2, which it seems like we should just be able to box up number C or letter C and call it a day. We need to check with extraneous solutions with something like this too, because log functions, remember, have a domain of only positive values, meaning you can only plug positive things into our log function. Not that these have to be positive, but when you plug it in, they have to come out positive. So if I plug in a negative 4 and square it, that comes out positive, so that's fine. If I plug in a negative 2 and square it, that also comes out positive. Let's check these. Negative 6 times negative 4 is positive 24 minus 8, so that's positive, so that's still fine. And then negative 2. Negative 6 times negative 2 is 12 minus 8, that comes out positive, so that's fine. What we're double checking is to make sure that this stuff on the inside is positive when you plug in these answers. All right, so they both turned out to work, no issues with the domains, that would be letter C. All right, as our second part here, we're going to look at logarithmic inequalities. Okay, so we have property of inequality that we're going to work with here. Keep in mind, like I said, we do have this domain restriction, and that's going to come into play here. So we can say that, first of all, we've got to have a certain restriction on our base, and that actually goes back to the restriction that we had back here. So b has to be a positive number other than 1, so we still have that exact same restriction. All right, so we can say that if log base b of x is greater than y, so you could start out like that, or if log base b of x is less than y. So we're going to have two different scenarios that we could start off with, and we're going to have one of each right here. So this means then x is greater than b to the y. So we're kind of translating back and forth between log form and exponential form. Just be careful. This one, then we could say that x, I'm going to leave a space here, I'm doing it on purpose, x is less than b to the y, but remember x also has to be positive, so we could say that x also has to be greater than 0. Here, if we're saying it has to be greater than b to the y, we're also guaranteeing that it has to be positive because b to the x is going to be positive. So here we have to enter in this domain restriction. All right, so be very careful with that. So let's take a look at example 3. We've got parts A and B here. So this one, if log base 6 of x is greater than 3, we start with the x, and we say that it must be greater than, and then we convert the rest of it into exponential form. 6 is our base, and 3 is our exponent. Okay, so simplifying this up, we say x is greater than 6 to the third power is 216. All right, so this, remember, log base 6 of x, that represents an exponent. So this is saying if we want the exponent on 6 that gives us x to be bigger than 3, then x would have to be bigger than 16. Because in order for the exponent on 6 to be bigger than 3, it would come out to be something bigger than 216. All right, so this would be our final answer here. There's no need to put the domain restriction on here because if we're bigger than 216, we're guaranteed to be bigger than 0. This one is where we bring in the domain restriction. So we start with the x, and we keep whatever sign we have right here, and then we convert the rest of it into exponential form. So our base is 2, our exponent is 4. So we're going to be less than this number. We need to make sure we're holding with the domain restriction, and we've got to say that x has to be positive. Okay, again, the reason that we don't have to write it here is because if we're bigger than 216, we're definitely bigger than 0. Here, because of the less than, we need to make sure we write it. We never have the or equal to. Our domain restriction is strictly greater than. So this we have 0 is less than x, which is less than or equal to 2 to the fourth, which turns out to be 16. All right, so this is saying if I want my power on 2 that gives me x to be less than 4, if I put a power on 2 that is smaller than 4, I'm going to get a number that's smaller than 16. But it has to be bigger than 0 because no exponential function will ever spit something out that's smaller than 0. Okay, this last one, example 4, you're going to be solving another inequality. And this one seems like it should be super easy, but it's got a little bit of kind of an added twist in here. So notice how on both sides you've got the exact same base. You have log base 7, log base 7. So it used to be with the equations that you could just immediately set the insides equal to each other, and you can sort of do that. Let me explain what the twist is. So you start with that. You start by saying like, all right, so we know the base parts are already the same, so it must be that this inside is greater than this inside. So let's start with that. And then we solve that just like a normal inequality. So I'm going to subtract the x from both sides, so that'll cancel. And then I will also subtract this 8 over to the other side, so that will cancel. So 2x minus x is x, and then greater than 5 minus 8 is negative 3. So like that's part of the answer, but not the entire answer. The last thing that you need to remember with these is that logarithmic functions have these domain restrictions. So you're not allowed to plug anything in that isn't positive. So you also have to make note of the fact that the 2x plus 8 has to be something positive, and the x plus 5 has to be something positive. So then solve those little equations, those little inequalities, and then we'll be able to combine them all up for our final answer. So subtract 8 from both sides, divide by this 2, and then we have x is greater than negative 4. And for this one, you'd have x is greater than negative 5. So basically, we're looking for the overlap of all three of these sets. So to be greater than negative 3 actually already encompasses both of these groups. So to be greater than negative 3, everything in this group automatically falls in this group, and then everything in this group automatically falls in this group as well. So the overlap actually does just end up being x is greater than -3. But you need to be careful because there are plenty of situations where the inequality might go in a different direction. Like if one of these, if this was a less than, perhaps, then the whole thing would change and you'd have to look for the overlap. So don't forget about the domain restriction by taking the inside pieces and making sure that they're positive.